Good morning. I'm Jeff Young from the ARM HPC Users Group, and I'm happy to be able to speak today with Ben Bennett from Hewlett Packard Enterprises. Ben is a HPC marketing and strategies working in the EMEA organization in the UK. Ben also works with HP's corporate affairs team to drive HPC content and knowledge into their works with the science, research, and industrial components of public bodies. Today, Ben will be talking about some of the lessons learned from Catalyst UK. Thanks for being with us, Ben, and please go ahead.
Jeff, it's a pleasure. In this talk, I'm acting as my role as the Director of HPC Strategic Programs. The Catalyst UK is one of the programs that I look after. So we'll dive straight in. So Catalyst UK, I'm hoping that everybody knows what Catalyst UK is. If you don't, then Catalyst UK is a 3-year program. It was work undertaken by Hewlett Packard Enterprise, the Department for Business, Energy and Industrial Strategy in the UK government in the winter of 2017, and the program was announced on April 2018. The first systems were deployed at the end of 2018. The process of, or rather the importance of Catalyst UK was seized upon by many people within the UK, ARM being a UK company, and the partners, which is ARM, Hewlett Packard Enterprise, Marvell, SUSE, and Mellanox, were putting a program together to deploy 3 systems focusing on different aspects of the ARM software ecosystem. Those sites were the Edinburgh Parallel Computing Centre, attached to the University of Edinburgh. Please, Dr. Wieland will be presenting to you later. I can thoroughly recommend her talk. The University of Leicester, as its in its role as host of DIRAC, and the University of Bristol, which many of you know from its work with ARM, and it also has the Isambard system, which is a Cray-based ARM system. As I say, the purpose of the program was fundamentally to grow the software ecosystem, to make sure that we looked at applications and system software, as well as the thing that everybody expects us to do is to port applications, work with ISVs, make codes faster, take advantage of the memory subsystem. Systems themselves, 64 nodes, each with 2 Cavium, later Marvell ThunderX2 processors, so 64 cores, a fairly large amount of memory. We have 7 service and storage nodes. 3 of those storage nodes are connected to SAS enclosures with both hard drives and solid state drives. And the thing that's important from, or was important from HP at the time, is we wanted to make sure that our entire software portfolio ran as well on ARM as it does on AMD, Intel, or standard x86. And we've worked very hard to bring the tools up, but there's nothing like deploying systems with a variety of users to help do that. When I checked last week, we had no open bugs against any of our tools, but having said that, I'm sure that there will be some between me recording this and you hearing it. We were very grateful that this time last year that the HPC community recognised the work that we've done, and we won the HPC Wire Award for the best academic government industry collaboration, and play spot your favourite person from that motley crew on the right. The four of us on the bottom are Simon Burbage from Bristol, Mark Parsons from Edinburgh, Mark Wilkinson from Leicester, and myself from HPE. Other people you'll see, Pete Ungaro, Bill Manell. Oh, and now I'm going to be embarrassed because I've forgotten Tom Taber's name, who runs HPC Wire, Jay Krumke from SUSE, and David and Brent from ARM. So there are, as I said, there are 3 sites. The first system that went in was the Edinburgh Parallel Computing Centre, and it's been the lead OS vehicle. And I don't mean the most important, I mean the people that have been prepared to take the most risks. So they were the people that we experimented with to go from SLES 12 to SLES 15. They're the ones that have done the work on Slurm, and they've created luster pools of both hard drives and solid state devices. They've made these changes to the system that was shipped so that they can do more work and they can plug in a variety of configurations in terms of CPU frequency, SMT modes, to see how the applications work. They've done single node studies and full 4096 core system runs. Of course, you would expect them to have done things like high performance conjugate gradient stream, Castet lamps, in Compact 3D, the list goes on. And looking at the number of threads per core, which is Marvell's SMT modes and memory system turbos, CPU frequencies, and importantly for us, power measurement. There was a lot of talk that ARM was going to provide you with performance for less power. We've tried to downplay that, because if you're flicking on all the transistors on and off for high floating point intensive operations, then you're going to consume the current. A well-known engineer once said, "You cannot change the laws of physics, Captain." EPCC have taken a lead in deploying Lustre on ARM servers. We talked about homogenous at the first opening of this, and these systems, these HPC systems, are not like other ARM systems. We haven't dropped a pile of compute into an existing infrastructure that has, you know, Lustre servers that you can just connect to. Well, we have, obviously, because they've all gone into high performance computing environments. But one of the things that we wanted to do was to host Lustre on the storage nodes. And this has not been done before. We've had issues with a lack of support for the Lustre driver. It's not officially supported by SUSE. Performance and reliability have both got room for improvements. And the euphemism is drivers need to become more mature, is that we still need to do a lot of work. The configuration is such that we haven't been able to get Lustre working reliably over the InfiniBand using the operating system and what we have. And this is a question of an amount of man hours, women hours, person hours that you put into fixing this. EPC want their system, Fulham, to be used. And so, as well as it being able to support scientists, they've done some COVID work over the summer, which is not to belittle it. It's also, we can't spend all our time playing with the systems. We need to improve the ecosystem, but real work is what improves it. So if you want more details, then please, go and look at Michelle's detailed presentation. So other sites, well, one of them is Bristol. Firstly, we have to send out our wishes to Simon Burbage, who is recovering from COVID-19. And I'm in two sort of minds here about wishing him recovery so I can nip down to Bristol and thump him because he wasn't able to provide an up-to-date update for me because he was sick. I'll let him off. Currently, the system is undergoing an upgrade to SLES SP2. It's been running on SLES 12 without any problems. But the reason it's being upgraded is that the system is having added nodes, a new switch to support NVIDIA GPUs. There was an announcement at Supercomputing about 11 months ago about supporting NVIDIA GPUs. And when I spoke to our engineer on site, Pete Guyan, there were issues with some of the drivers. So that's being worked. Simon did want to point out that there's certain stuff that's gone on. He wanted to highlight the published work on cryo-electron microscopy, some of the modeling has been done on the ARM system. Pardon me. Oh dear. Purely a throat issue, I promise you. Yeah. Going back to Bristol University, they have a very well-renowned code called BUDE, which is about protein docking. It's about how molecules interact, and this code makes use of GPUs. And this is going to be the focus of the work that Bristol do moving forward. One of the things that we're starting to see is that it was initially easy to get the systems up and running. But as you make changes to the system, then the ramifications ripple through the system. And what we're seeing is, obviously, there's not been, because I'm just going to repeat myself here, there's just not been enough cycles to do this. So it doesn't stop the systems being useful. In fact, our friends at Leicester have been very happy with the systems. They too are upgrading the system to SLES 15 Service Pack 2, and they are also adding NVIDIA GPU nodes. They have a bunch of Earth observation data that comes in, and they're very interested in utilizing the memory bandwidth and to start using the GPU nodes. Sorry. Again, it's being used to support COVID-19. So Dr. Andrew McCullum, who works in the Aerospace and Computational Engineering Department of Leicester, has been using open foam, look at room ventilation, as you would in a medical setting. How do you make sure that you move particles away from people? It's also being used at the UK Atomic Energy Authority. And it's doing the sort of things that you'd expect it to do there. It's doing finite element modeling, Monte Carlo CFD, and the general feedback, from oh, I've just noticed they're both called Andrew, from the Andrews is You know, it works in much the same way as any other supercomputer, which is goodness. You don't want it to be problematic. And that the people at the UKE found that access had been incredibly useful. So it's nice that we're able to provide a tool that the scientists can use, and that it's not hasn't been a big step, just looks like an ordinary computer. So this says what's next, but it also should say, you know, what do we need to do differently? And part of what we need to do differently is we need to better understand the gaps in the system software and the interactions between the various components, such as InfiniBand, the NVIDIA drivers, SLAERS, Lustre, and all those other things. And we need to do some more work on that. This will be done as we do more application porting and more system tuning, and as we do the NVIDIA GPU experimentation. If the majority of the code is going to run on a GPU, then a lot of questions have been asked about the power consumption of the host CPU. How much work is the host CPU doing? And therefore, can we utilize a lower power host? We've learned a lot. And so we will be documenting, disseminating the system admin information regarding the support of the operating systems. And we hope that people will, you know, look upon ARM as just another supercomputer and an option. And we'll do the same thing with the application porting and tuning. Now, we're very aware that the world's fastest computer right now is ARM-based. It has a slightly different vector engine than the Thunder X2, and the codes are slightly different. So we need to look at that. And I know that the University of Bristol will be doing that with a machine they're getting sued called Isambard 2. There's been a lot of learnings in that HPC is not the market to rush out and make lots of money in. There's the old joke that the way to make a small fortune in HPC, the way to make a small fortune in high performance computing is to start with a large one. And we have seen changes. We've seen Marvell change their focus. The original system was not going to be all Marvell processors. The I/O was going to be based around a separate low power I/O intensive ARM processor, and that got pulled even as we were trying to ship the systems. So they really did become very homogeneous. So where is the focus? I think the Fujitsu processor is very interesting. I've seen some work by the SUSE people looking at the Ampere processor, the I/O processor. It's got good I/O. And for that sort of application that isn't compute intensive, it is actually very power efficient. So where do we go from here? What happens next? We believe the machines will get turned over for production. You know, they're there, they're science. We want to see the science. A lot of people have asked, is there going to be a catalyst too? Well, if there is going to be a catalyst too, we shall obviously have to look at CPU vendors, I/O, different software, different architectures. And all of this is to be determined. We've got a year to run, and we'd like to get all that information and get it disseminated to the community so that they can learn from this experiment. So with that, I'd like to thank you for your time. And Jeff, back to you.
Thank you, Ben. That was a very exciting update on the state of the Catalyst project. I had one or two questions. I know obviously our viewers will probably have questions as well. And we'd like to remind you that we'll have a panel on November 9th, and hopefully Ben or someone from the Catalyst project will be able to make that panel. But I just wanted to ask you, Ben, you mentioned that there were these great benefits in terms of using the Marvell TX2 type architecture, but there were also these struggles with implementing things like InfiniBand drivers and Lustre drivers. Did you find that each of these sites having very similar systems, did that actually help in terms of actually debugging these issues and saying, okay, maybe at Bristol we could work on solidifying driver support for InfiniBand and then migrate that to the other sites? And were there any examples of that where you kind of saw this cross-pollination in terms of sysadmin and driver expertise?
Yeah, absolutely. We have a regular call, which is hosted by SUSE. They've been very good. We've had excellent collaboration with Mellanox, as well as technical support from Marvell. Yeah, so we get together, we share. There's been a core handful of people from HPE that have been assisting. As I say, we did most of the bashing initially on the Edinburgh machine. We had a week, I think they called it a fixathon, where we had a whole bunch of technical support from HPE, Mellanox, SUSE, who did I forget? Marvell. And these people got together and we started to hack through the list. Now, as we move on to the NVIDIA drivers, then Edinburgh are not going to be doing that. They're looking at power. So yes, I expect the work that we are doing now at Bristol will be extremely beneficial for that at Leicester. So yes, we do share information. There is a repository of that information, and having 3 sites clearly means that you can make and find 3 times as many errors, and hopefully fix it much quicker.
Right. Great. And just one more question.
Sure.
We sort of have seen this kind of consolidation of some of our IO and GPU vendors, especially with Mellanox and NVIDIA joining forces. With this push to kind of support GPUs, do you think is that kind of a beneficial move for supporting ARM compute processors in the future? Does that help us in terms of actually deploying these systems that have both CPUs, GPUs, and InfiniBand networking?
I have to be very careful here. I've been looking at some of the results that have come out of Fugaku, which is another almost homogeneous machine. It doesn't have dedicated accelerator hardware, and it's very efficient and it's very good. I am aware that there are certain things that GPUs do very well. The biggest step is to get them to talk to the same memory as the CPU without having to go through the bus. We know that's happening. We know that's coming. And I think that is going to unleash the power of GPUs. I think where ARM fits into this is that the ARM system, it's a lot easier for people to take a problem and to find a better solution deploying an ARM processor. It's, there is a variety. There are very specifically IO focused devices. There are very specifically compute-focused devices, the stacked memory coming, and there's a range of the vectors are coming back. For those of us who are closer to 60 than many other birthdays, are happy that vectors are coming back, because we can still write Fortran and its newfangled 77 variant that might or might not make any importance. Yes, I'm sorry. That was a very naughty of me. Everybody knows that Fortran 90 is the standard now. Yes, I think if you have work that can be done effectively by the GPU and doesn't need a lot of interaction from a main CPU, then why wouldn't you put an ARM processor in the front? The ARM processor, acts as the connection to the root complex, and you're away. I think we're in for very interesting times. I think there's been a lot of announcements about the exascale machines, the exascale technology, based around, big heavy CPUs and big heavy GPUs in certain ratios. I think that Fugaku is going to make people stop and think about what they are trying to do in terms of what they want. And that in no way is going to impact whether or not people need GPUs. Yes, people will need GPUs and they will go forward. I think, it's interesting times. It's nice to have a variety of processor technologies that allow you to build a system that better matches the problems you're trying to solve.
Great. Well, that's a very exciting to look forward to. Thank you very much for your talk today, and thank you for your time.
Jeff, thank you very much.